friends, today we will discuss combination of capacitors, energy stored in capacitor, energy stored in combination and common potential. So a lot of things we will discuss today. So we will not do later. Let's start combination of capacitor first. Combination of capacitor. So combination of capacitors we will discuss today. You have read in class 10th combination of resistors. Resistors are how they combine in class 10th. They can combine in series as well as they can combine in parallel. The same thing also we will discuss here. Series combination of capacitors and series combination of and parallel combination of capacitors. Let's first start from series combination. Series combination of capacitors. Let's first start. Capacitor symbol. I have told you this is the symbol of the capacitor. Two bars should be of same height. Then this is the capacitor. Okay. But in series combination, what happened? Capacitor one plate is plus, one plate is minus. In series combination, this minus plate of one capacitor is connected to plus plate of other capacitor. It is like this. Minus plate of one capacitor is connected to the positive plate of other capacitor, and so on. If we do for 2, then this is now we'll discuss. We'll do this derivation. We will find the effective capacitance for two capacitors of different capacitance C1 and C2. In resistor series combination, you know which quantity remains constant. Current remains constant in series combination because that is one path. One path, so current remains constant in resistor combination in series. So here in series combination, charge remains constant. Charge of this capacitor is the same as charge of this capacitor. Okay. Then what happens to the potential difference? Potential of each capacitor? Potential divides. In series combination, always potential divides as also in resistor. In series combination, potential divides. If this potential is V1, then this potential is V2. Different potential. Now I will find what is the effective capacitance. If both of them behave as one capacitor, then what will be the effective or what will be the net capacitance? If suppose they behave as one capacitor, then the capacitance, net capacitance is C. I am writing here S. S stands for series combination. Then the potential is V. Okay, let's connect it with a cell. If the cell is connected, cell potential is V. If cell potential is V, then this potential is V1, V2. Then V potential divides in them. That means V is equal to V1 plus V2 because potential divide. Okay, but charge is Q charge. And here I will connect the cell. This is the capacitor. Okay, I will connect the cell here. So this cell I have connected here. This is V potential. So here the capacitance is CS, the effective capacitance of these two capacitors. Okay, so now let's find what is this effective capacitance expression in terms of C1 and C2. So this expression now, if you write for this capacitor the relation C1, C is equal to Q by V, Q by V1 for this first capacitor. For second capacitor, if you write C2 is equal to Q by V2. So here V1 is how much? V1 is equal to Q by C1, and here V2 is how much? Q by C2. But for the combination if I write, okay, for the combination if I write, then CS is equal to Q by V. CS, Q, charge both same. Okay, so CS is equal to Q by V. That means V is equal to Q by CS. This is for the combination. This is for the individual capacitors. Now as potential divides, then what to write here? As potential divides, you see V is equal to V1 plus V2. So what is V? Q by Cs. What is V1? Q by C1. What is V2? Q by C2. So 1 by Cs is equal to 1 by C1 plus 1 by C2. So this is the expression for effective capacitance in series combination. What expression is coming? What you will compare with your 10th class? Your 10th class, what was the expression of in series combination in resistor? R is equal to R1 plus R2. But parallel combination is 1 by R is equal to 1 by R1 plus 1 by R2. So what is the parallel combination formula in resistor? That is the series combination formula in capacitor. So it's easy to remember. Okay, you can now reverse the formulas. You can able to remember now. Okay, so this expression also you can remember easily. This one you take the LCM. If you take LCM, you will see C1 C2 CAC, you will get C1 C2 by C1 plus C2. You remember when two capacitors are there, you just remember this formula to solve the questions. Effective capacitance is just taking LCM, I got it, C1 C2 by C1 plus C2. But if many number of capacitors will be connected similarly, then 1 by Cs is 1 by C1, 1 by C2, 1 by C3 plus dot 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 dot, it will continue like this. This is about the capacitor connected in series. Now let's come the capacitor connected in parallel. We will come to parallel combination now. Let's see what happens in parallel combination. We will again draw two capacitors in parallel combination. So this is one capacitor and this is one capacitor. In parallel combination, both are connected to a cell. Okay, so this is cell, potential provide V, then here potential will be V, here also potential will be V. In parallel combination, what remains constant? Potential. You also know this in class 10th. When the resistors are connected in parallel, what remains constant? Potential, because difference remains constant. Why potential difference is constant? Because their end points are same. Here, suppose this point is A, this point is B. What is the potential difference of these two plates? VA minus VB. What is the potential difference between these two plates? VA minus VB. What is the potential difference of the cell also? VA minus VB. In parallel combination, the end points are same. For that reason, potential difference is also same. But here charge is supposed to provide Q charge. Here charge will be Q1, here charge will be Q2, its capacitance is C1, its capacitance is C2. Now we'll see what is the effective capacitance in parallel combination. Okay, when these two capacitors are just treated as one capacitor like this is the effective capacitance. Cp, I write the symbol for effective capacitance in parallel. So this is V, this is Q, here also V, here also Q, charge. Okay, so total charge is Q charge provided. So combine Q1 plus Q2, that is equal to Q. Okay, so this says as this is effective capacitors, combination of these two behave like this capacitor, I don't have Q. Okay, so now I write for the first capacitor, again the formula C1 is Q1 by V, and so you find Q1 here, C1 V. For second capacitor, C2 is Q2 by V, so Q2 is equal to C2V. For the combination, again Cp is equal to, so Q by V implies that Q is equal to Cp into V. But here charge divides. As it is parallel, potential remains constant, but charge divides. As charge divides, Q is equal to Q1 plus Q2. What is Q? CPV. This is CU1V. This is C2V. Q1. Q2. From here I got Q2. You see now VV cancel. So Cp is equal to C1 plus C2. This is the effective capacitance in parallel combination. If many number of capacitors will be connected, it will continue like this: C1 plus C2 plus C3 plus C4 plus C5 plus C6. Okay, well, not tell you more. So this is about parallel combination of capacitors. Now you understand? Now we go to the energy stored in capacitor. But one thing you now able to mark, I told you the series combination of resistor formula is same as the parallel combination of capacitor. Parallel combination of resistor formula is same as series combination of capacitor. Just reverse formula, just reversed. Okay. So now let's see energy stored in capacitor. This comes as a small derivation in exams. Energy stored. Energy stored in capacitor. Now we'll discuss. This comes as a small derivation of 3 marks in exams. It's a very important one. From the second chapter, it's a very important derivation. The first important derivation of second chapter is this: energy stored in capacitor. Okay. First the question comes, why energy is stored in capacitor? From where this energy comes? I have told you one thing. When a body moves automatically, what happens to its potential energy? Decreases. Automatically, when the stone moves in the downward direction, automatically it moves. It moves by the field. By the field, then its potential energy decreases. But when you take the stone against the force, means from down to up, from ground to first floor, what happens? Its potential energy increases. So I had told you this one before. When the potential energy of a body increases, if some work is done against the force, against the field by external agent. Against force by external agent, when work is done, then energy is stored in a body. Energy increases. Energy stored. But here, what work will do against what will do the work so that energy is stored in the capacitor? You see? So this is the capacitor here. This is the capacitor. Okay. So from the starting, its charge is 0, its potential is 0, then capacitance is 0. 0? No, capacitance is not 0, because capacitance is constant. It doesn't depend on how much amount of charge you have given to it. It doesn't depend. Whenever in doubt is coming in capacitor, you just compare the capacitor with the water tank on the top of your roof. You just compare top of your house, water tank is there. Your water tank capacity is 2000 liter. Suppose now due to some problem water is not there. Okay, so supply water is stopped for some days, water is not there in your water tank. That means its capacity is 0? No. Water tank capacity is 2000 liter. Water may not be there. Suppose you use half of the water, means its capacity becomes half. No, capacity is constant. Capacity doesn't depend how much amount of water is there. Capacity doesn't depend how much amount of charge is there. This is one important concept to remember. Capacitance is a constant. It doesn't depend how much charge is there. So its charge is 0, so potential is also 0. But its capacitance is fixed. Once capacitor is made, means capacitance is fixed. It depends on its geometry. Epsilon A by D, area of cross section, its distance of separation, medium between it. Okay, so this is about the first condition. It has some capacitance but charge 0 and potential 0. Suppose now we give some amount of charge. How much charge will give? Now I get Q amount of charge to it. To the capacitor Q not I will give. Who will give to the capacitor? External agent. Who is the external agent here? Cell. Cell is the external agent. You will understand after some chapters of how cell gives charge to a capacitor in one chapter called alternating current chapter. But you now remember here only cell provides charge to the capacitor. Cell is used to charge the capacitor. Okay. So now Q amount of charge cell has given to it. Its potential is raised. Now the potential difference between the two places is maintained as V and capacitance is C. There is no problem in capacitance. So C is equal to now Q by V. Okay, now this is the condition. Clear? If I will add some more charge to it, now the question is coming, how much more will I add? I will now add here dq amount of charge. I will add dq amount of charge to it. If I am going to add a dq amount of charge, then what happen? This existing q will not allow this dq to be added. This q will not allow this dq. You see, because this q is here. Suppose I have added some charge there, plus 1 coulomb. When I take another plus 1 coulomb, it will not allow. So q is here. When I am going to add dq, then this q will not allow this dq. Then what we have to do? We have to do work. Cell has to do work against this q, against the force and repulsion of this q. Against q, we have to do work. To add a dq amount of charge, we have to do work. So now how much work we have to do? Our cell has to do how much work? That work is stored in the form of which energy? Energy stored always means which energy? Potential energy. When some work is done against force, I told you which energy increases? Potential energy. But here which potential energy? Gravitational? No. Electrostatic potential energy increases. Where this energy is stored? Question may come like this. Where this energy is stored? Between the two plates of the capacitor. In the form of field also. More and more charges when added, then the electric field between two plates. You see, this is the plus plate, this is the minus plate. Initially, some charges are added. Very few charges are added. Electric field is like this. When the charge increase, what happens to the field? Now field increase. When again more charge given, what happens to the field? Now field increase. You see, field increase. Okay? So the energy is stored between the two plates of the capacitor in the form of electrostatic potential energy. Remember this one. Okay? So between the two plates of the capacitor. So now you understood why work is done and how the energy is stored in the capacitor. Okay. So when this dq amount of charge is added, you have to work against this q. You have to move this dq charge in the potential difference V. Then how much amount of work is done? That is the potential energy added to the capacitor due to the addition of dq charge. Okay, now how much work is done here? Now let's see. So potential difference was initially V. How much amount of work done? Very small work. If you are adding small charge, also I will write work is also small. But W is Q into del V. So Q. But Q means which charge is moving? dq. Okay, Q dq is moving. So Q into del V. Del V, what is the potential difference? V. So this is the formula. Why don't to add a dq amount of charge? Is this the formula? But to add a capital Q amount of charge to it, suppose I will add a capital Q amount of charge total from 0 to capital Q. Initially there is no charge. Now how much amount of charge will add? Capital Q amount of charge will add. Capital Q amount of charge will add. Now what will happen? Suppose this potential rises to capital V. You treat this as small v. This potential rises to what? Capital V. When charge Q, potential small v. When charge capital Q, potential capital V. Okay, so now charge. Now this is the work done to add a dq amount of charge. We will find the work done to add capital Q amount of charge total, starting from 0 to Q. How I will find? How I will find it? I have to do integration. Now I will do the integration. You see, I have to do the integration here. I will do the integration here. So dw integration 0 to w, then dq into v integration, then 0 to capital Q. 0 to capital Q. Okay, because charge we have to add. Initially there is no charge 0. Finally the charge is capital V. So 0 to capital V. 0 to Q. Finally the charge is capital Q. So 0 to capital Q. Okay, so now let's do the integration. dw integration is w and limit if you put w. Here what happens? V comes to outside. dq integration is Q. Okay, then the limit limit is 0 to q. Then it is coming v. In place of this you put upper limit, this coming as vq. Okay, v comes to outside of integration, q, vq. Understand? What happened? Is there any mistake I have done? Yes. So in which way I did, this is the common mistake. You will not do this common mistake. I now from v I have taken to outside of the integration. I cannot take v outside of the integration. Why? Because v is not constant. When charge increases, potential also accordingly increases. Directly proportionally potential increases. So it's not constant. So what happens here? You cannot bring v to outside of the integration. You cannot also do the integration. Why? Because v is one variable, q is one variable. But we can do. How? You will convert one variable. You will convert v in form of q. How will you convert v in form of q? You see here. You see the formula? So v is equal to q by c. Now put here v is equal to q by c. 0 to capital Q. 1 by c is taken to outside. Q due q integration you know. Q square by 2. X to the power n dx integration is x to the power n plus 1 by n plus 1. This formula I used here. Power is 1. So n plus 1 by n plus 1. 1 plus 1 by 1 plus 1. 0 to q. Then you put the upper limit now. If you put, then you will get q square by 2. So q square by 2c is the work done. If this is the work done to store 0 to capital Q amount of charge, then what is the potential energy stored here? That much amount of work done is stored in the form of potential energy. So potential energy here, U is equal to half Q square by C. So this is the potential energy of the capacitor, stored in the capacitor in the form of electric potential energy in the space between the two plates of the capacitor. But we can write this expression in different form. In which form I can write this? I wrote in the form of C and Q. I can also write in form of C and V. Let's see in different form. In place of Q you put CV. This V is the final potential. This V is the final potential after being charged. After when capital Q amount of charge is stored, this V is the potential. Okay, what I told you, capital V, like this. Half CV square. So this is also another formula. You can also use this formula. Let's go to another formula. Now QC form, CV form. Now let's do QB form. Why will I do that one? Let's do QB form. Okay, how do QB form? So half, in place of C you put Q by V. In place of C I put Q by V. So it is coming half QV. This is also electrostatic potential energy stored in the capacitor. So how many formulas I wrote here now? You see 3 formulas of the energy potential energy stored in the capacitor I write. You understand? Let's see one thing. If I draw QB graph, suppose here I will take Q, here I will take V. Let's do the graph. How was the graph? I have told you in the previous video, the graph is a straight line. Starting from origin, because both are direct proportional to each other, but the slope of the graph gives, I have told you while finding slope always do y by x. Y by x. Q by V is C, capacitance. Q by V is capacitance. Okay, so slope of the graph provides you capacitance. I have told you. Also, I had asked you one question. If this will be V, this will be Q. Then it gives reciprocal of capacitance. And what is the name of what quantity? What name is given to reciprocal of capacitance? I hope you already got the answer. That is elastance. Reciprocal of capacitance is called elastance. Okay, just like your reciprocal of resistance is conductance. Then now let's see what is the, how can you find energy stored from this graph? Energy stored in the capacitor from this graph. You see, this is the graph. Let's see the area under the graph. This is the area under the graph. It's coming as a one right angle. Now you see this now one triangle, right angle triangle. What is the area of this right angle triangle now? It is a half base into height. This is the base and height is Q. This is the area. This is the area under the graph. And this formula both are same. Oh, this is the point. Then the point is area under QD graph provides the value of potential energy stored in a capacitor. This line you note, it's a very important line. Area under QD graph provides you potential energy stored in a capacitor. Okay, so this is about potential energy. When energy is stored, where this energy is stored? This energy is stored between the two plates of the capacitor. Then we have the curiosity to find the energy density. What is the energy density then? Now let's see the energy density. When this energy stored comes in exam, it must comes with this tell question. Also find energy density. If energy stored will be 2 marks, energy density will be 1 mark, total will be 3 marks. So we will not leave this one, we will also discuss energy density. Energy stored in the space between two plates of capacitor means that's a volume. That's a volume between this space. This is D, this is A. What is the volume of the space between them? It's a very clear, area of cross section into distance, A into D. So energy stored, symbol I am writing small u is equal to energy divided by volume. But what is energy? Half CV square. What is volume? A into D. Volume is A into D. Then half, here you can put in place of C, epsilon naught A by D capacitance. Then in place of V you can put E into D, electric field. Relation between electric field and potential difference we have done. Okay, V is equal to E into D. Then is equal to, now you cut what is possible into D. Then y left you A into D here. A into D also was in denominator. A cancel, D square cancel. Epsilon naught U square. This is the energy density of the capacitor. Half epsilon naught E square. Remember this one. Again this expression after some days also I will tell you to recall. Okay, this one also will be used in other chapters in the next chapters. Clear? So this is about energy stored in the capacitor and energy density. Now let's see here. In combination, what happens to the energy stored? When suppose 3 capacitors, let's see first series combination. Energy stored in combination of capacitors. In combination, energy stored. This is one capacitor. This is one capacitor. Series combination. Let's do series combination. Its energy is U1, its energy is U2, its energy is U3. Suppose energy stored in the 3 capacitors are U1, U2, U3. Their capacitances are different, C1, C2, C3. Then what is the total energy stored? Series combination. What is the total energy stored? Just guess. Series combination. What is the effective capacitance? 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. What is the total energy stored also? 1 by U is equal to 1 by U1 plus 1 by U2 plus 1 by U3. Is it like this? No, not like that. Okay, so let's see what will happen. We'll prove, then we will confirm about this. Okay, so for first capacitor now let's this is series combination. What remains constant here? So charge remains constant. Q. For the 3 capacitors, Q is the same. So for U1 now write the formula half Q square by C. C1. I wrote this formula because Q remains constant. For why? I wrote this formula now. For the second one, half Q square by C2. For the third one, half Q square by C3. Let's add. Now this is the energy stored. So what is the total energy stored in the combination? When if they behave as one capacitor, for the total energy stored U, let's write US. Series combination total energy stored. Okay, US. Effective capacitance is C. and the effective total charge is Q. Okay, then what happens here in the effective case? US is equal to half Q square by CS. This is series combination. Okay, so now let's see what happened here. If we, okay, this is from this you start. Half Q square by CS, half Q square. This is 1 by CS. I split it like this, 1 by CS. Now you see half Q square 1 by CS. What is the formula in effective? This capacitance formula in series combination: 1 by C1 plus 1 by C2 plus 1 by C3. Now you just multiply inside the bracket half Q square by C2 plus half Q square by C3. What is this? U1. What is this? U2. Then what is this? U3. So what is the total energy stored? Simple addition of energy of the different capacitors in series combination. Let's see what happened in parallel combination. Now let's come to parallel combination. What happens? Let's see parallel combination. Okay, so parallel combination. This is the one capacitor, another capacitor, another capacitor. So all are connected in parallel. Okay, so here potential divides, but here potential same. V. Parallel combination, so potential same, but energy stored U1, here U2, here U3, capacitance C1, C2, here C3. And the combination, when both behave, all behave as one capacitor, then the effective capacitance Cp, potential is V. Okay, potential is V, and the total energy stored is Up. Parallel combination, so I wrote here P. Now let's see. For this one, you write the formula for first capacitor. Un is equal to half C1 V square. Then you are thinking, sir, why you are writing this type of formula? In the previous one, you wrote the formula half Q square by C, but here you are writing the formula half CV square. All the formulas are same, but I am writing which one will be easy for our derivation. Accordingly, why I wrote there in previous one series combination, why I wrote Q square by C? Because they are Q constant. But why I am writing here half CV square? Because your V constant. It will be easy for our derivation. Okay, then U2 half C2 V square, then U3 half C3 V square. Then for the combination, UP half CP V square. Then now see here, half, this is the effective capacitance in parallel. So C1 plus C2 plus C3 into V square. So it is coming half C1 V square half C2 V square half C3 V square. Okay, what is this? You see, this is U1. What is this? U2. What is this? U3. So this is the effective capacitance in parallel combination. Effective, this is total energy stored in parallel combination. Understand what happened? Irrespective of the combination, this line is now important, you can write. Irrespective of the combination, total energy stored is equal to sum of energy stored of individual capacitors. Connection may be series, may be parallel, but total energy is equal to sum of energy stored in the capacitors. So now this is about the energy stored in the combination, and the last part will go. Last part is now common potential. We'll discuss now common potential. Okay, so before discussing this one, if I'll ask you one question, now you can tell me the answer here. Suppose two water tanks are there. Two water tanks. Tank A, tank B. Tank A, tank B. This is tank A, this is tank B. Tank A contain more amount of water, but tank B contain less amount of water. Okay, both tanks are connected by a pipe. Both tanks are connected by a pipe. Now they are interconnected. They are connected by a pipe. I am again telling, tank A contain more water, tank B contain less water, and both tanks are connected by a pipe. Then what will flow from which tank to which tank? What will flow now? From which tank to which tank? You are thinking the answer. What will flow from tank A to tank B? Because tank A contain more amount of water. So what will go from tank A to tank B? Yes? Okay. Now let's see. So tank A contain more water, tank B contain less water. What will go from tank A to tank B? It will connect a pipe. So tank A is here. It contains more amount of water. Tank A is here. This is tank A. And tank B is here. This contains less amount of water. Tank B is here. Both are now connected by a pipe. You see. What happened? What happened? Now you are thinking, sir, you are doing cheating. So you have not told from the starting that both tanks are in different heights. Okay? But what mistake you did? You just thought from the tank of higher water, in which tank more water is there, from that tank to this tank water will come. No, not like that. You just tell the answer like this so that nobody can cheat you. Water will flow from higher potential to lower potential. Then automatically it will be understood. Nobody can cheat you then. Water will flow from higher potential to lower potential. Okay, so you see, it doesn't depend how much water it contains, it depends which is at higher potential. The same thing I am telling you. Okay, the same thing I am telling you. Two capacitors. This is one capacitor, C1 capacitance, V1 potential, Q1 charge. This is one capacitor, C2 capacitance, Q2 charge, V2 potential. Now these two are connected. These two capacitors are now connected. I will connect them. Okay. What will happen? So suppose Q1 is more. Q1 is more, suppose. Okay. If Q1 is more and Q2 is less, then from which capacitor charge starts flowing? If both will be connected, then charge starts flowing. From which capacitor to which capacitor charge will flow? From C1 to C2, from Q1 to Q2, because Q1 is more. No. Now you understand what happened. Water flow from one tank to another tank if there is potential difference from higher potential to lower potential. Here also same thing will happen. Charge will flow, not more charge, not less charge. Rather flow you will see from more potential to less potential. Immediately charge started flowing from higher potential to lower potential. From higher potential to lower potential, now charge will come. And this process will continue till the potential is not same. When potential becomes same, then the process stop. Then the flow stop. And now both will have same potential. If they are connected, then the motion of charge will stop. And this is same potential is called common potential. That one we will discuss today. If two capacitors connected, then charge flow from one to another, from higher potential to lower potential, till the potential is not same. When potential is same, then charge stop moving. This one will discuss common potential. Another also thing I am telling you, I am just reminding you, 11th class you have read also same thing like this. One body having high temperature heat, high temperature, one body at high temperature, one body at low temperature. When you connect them, what flows? Heat flows from high temperature to low temperature till the temperature is not same. The same situation. Heat flow till the temperature is not same. Water flow till the level is not same. Charge flow till the potential is not same, called as common potential. Now the potential is common. Then what about the charge? Charge Q1 is not here. Now this Q1 from higher to lower potential charge move. So Q1, there is some change in Q1. So this charge become Q1 dash. This charge become Q2 dash. This capacitance becomes C1 dash. This capacitance become C2 dash. What happened? Again I did one common mistake. What mistake I did here? Potential become V same, and charge change and capacitance change. It's not like this. Okay, it's right. Capacitance will not change. I have told you, whatever may be the situation, if geometry will change, then capacitance will change. Otherwise, change in charge, capacitance will not change. Okay, capacitance will not change. This is C1 and C2. Don't make it C1 dash and C2 dash. Capacitance is C1 and C2. Now we'll go to see here. We'll find the expression of common potential. Clear? Okay. So what happened here? Now see some similarity. When before combination, this is after combination. Before combination, charge is Q1 plus Q2. After combination, charge is Q1 dash plus Q2 dash. Is there some relation? Yes. From where the extra charge will come, from where the charge will go? Nowhere, because conservation of charge, only those charges rearrange between the two capacitors. Charge can be neither be created nor be destroyed. Conservation of charge principle only used here. Conservation of charge, initially it was Q1 plus Q2. Now it is Q1 dash plus Q2 dash. But initially total charge is equal to final total charge. After combination total. But what is Q1? C1 V1. What is Q2? C2 V2. What is Q1 dash? C1 V. What is Q2 dash? C2 V. Now see here, from here you take V common. If you take V common, it is C1 plus C2. To imply that V is equal to C1 V1 plus C2 V2 divided by C1 plus C2. So this is the common potential. C1 V1 plus C2 V2 divided by C1 plus C2. Understand? This type of formula you have seen somewhere in class 11th. Like this format formula you have seen somewhere in class 11th. Can you recall where you have seen this type of formula? Yes, where you have seen? This is common potential. You have seen common velocity. Where? Collision. Well, one-dimensional, perfect inelastic collision. Two bodies comes with a different velocity, U1 and U2, they collide with each other and stick to each other and then move. When they stick, now they stick and move, so they have common velocity. What is the common velocity formula? M1 U1 plus M2 U2 divided by M1 plus M2. So I just recall your 11th class. Okay? So we are thinking, sir, don't recall 11th class topic now. 12th class is okay. Okay, so now let's come. What about the energy store? Yeah. What is the energy store now? Let's see. Initially, what is the energy? Before combination, what is the energy of this? Half C1 V square, V1 square. Then U2, this is half C2 V2 square. Okay. What happened? Half C1 V1 square. This energy is half C2 V2 square. Energy of the two capacitors. Okay. So now after combination, what happens? So what is the initial energy? Initial energy half C1 V1 square plus half C2 V2 square. But what is the final energy after combination? Half its capacitor energy is C1 V square. This one half C2 V square. So it is coming half C1 plus C2 V square. Okay. So now see half C1 plus C2. Then what about this? V square. So in place of V I can write common potential formula. C1 V1 plus C2 V2 divided by C1 plus C2 this is whole square. Then you can solve it more. This final potential you can solve it more. C1, C2, 1, C1, C2 cancel. So C1 V1 plus C2 V2 whole square divided by 2 whole into C1 plus C2. Okay, C1 plus C2. This is the final potential energy formula. Now see, before combination total potential energy, after combination total potential energy, does the potential energy decrease or increase or remain same? It should be same. Why? Because energy conserved. It should be same. Let's see. Let's check. Okay, to understand now, let's check. What we'll do here, I will check this. Now, if both potential energies are same, do the subtraction. If do the subtraction, if the subtraction will come 0, both are same. If the subtraction will come, suppose I will do the subtraction now, see, energy difference, I do UI minus UF. If it will come 0, both are same. If it will come more than, greater than 0, then UI is greater. If less than 0, then UF is greater. Now let's check. You will put UI here, half C1 V1 square plus half C2 V2 square. Then you put this one, C1 V1 plus C2 V2 whole square divided by C1 2 whole into C1 plus C2. Okay, this one. And solution is yours. You will do the steps here. Mathematics you have to do. You have to open this square. You have to do the mathematics, and in between towards the end it will come some a minus b whole square formula you will use, and finally you will get C1 C2 by 2 whole into C1 plus C2 whole into V1 minus V2 whole square. This much answer you will must get if you will solve it. Your job is to solve this potential energy difference. Okay, and you will get this much energy. What happens? Capacitance is never negative, it is always positive. V1 minus V2. If by chance it is come negative, square is there, so it is also positive, means whole term is greater than 0. If it is greater than 0, which one is greater? UI or UF? So UI greater than UF. What happens to our conservation of energy? Now potential energy decreases. Potential energy decreases after combination. Before combination energy was more. When you combine, energy decrease. What happens to conservation of energy? It is not possible. If conservation of energy will change. If conservation of energy will not valid, then everything in the whole universe will change. Whole physics will change. Then what happened? Yes, energy decreases. But conservation of energy, that doesn't violate. Conservation of energy is not violated here. Then the question comes, if energy decreases, then the decrease amount of energy, this value, decrease amount of energy, where it goes? If conservation of energy is not, it cannot be invalid, then where it goes? The decrease amount of energy. That energy, I will not tell you where that conservation of, where that decrease of energy goes. That is, I am leaving to you. You search the book. There is a question comes in exam. The decrease of energy, where it is utilized. Okay, where that energy goes. So that is up to you. You will search the book. I will leave this question for you to just make you to open the book to read it. Okay. So, and this formula, I am just reminding you this formula. You have also seen this formula in class 11th. Where? Same collision. There what happens? There what change happen? Change in energy also there. Kinetic energy. You know, in inelastic collision, kinetic energy is not conserved. Kinetic energy change happens. There the decrease of kinetic energy appears in the form of sound, heat like this. Okay? In collision, I am telling you. Here the change in kinetic energy formula. The similar formula. M1 M2 by 2 whole into M1 plus M2 whole into U1 minus U2 whole square. Same formula you have read in class 11th. Change in kinetic energy. Decrease of kinetic energy. So this is about many topics today we discussed. combination of capacitors, energy stored in capacitor, energy stored in combination, common potential, energy lost, so many things today we have discussed. You can solve your NCERT book. Example 1 example is 2.9. You can solve, that's a very important example. Also similar question is there in 25 number question of your NCERT book. Circuit question. But while solving that question, always remember, in series combination, charge remains same. In parallel combination, potential remains same. You can solve those two questions. Thank you.